Okay, in this video we're going to look at a solution to problem B1 from the 2019 Putnam exam. So let's look at the problem. So we want to let Pn equal to the following set. So it's the set of xy, where x and y are both integers, that satisfy the equation x squared plus y squared equals 2 to the k for some k less than or equal to n. So notice that's going to make P0 contained in P1, contained in P2, and so on and so forth, union with the origin. So we want to add the origin in there. And we want to find the following number, so we'll set it equal to a of n, and that'll be the number of 4-point subsets of Pn whose elements are vertices of a square. So there's a lot to parse here, so let's do some exploration to wrap our heads around what's going on. So let's say n equals 0, so that means P of n is equal to the origin union all integers x and y, where x squared plus y squared equals 1. Good, so it's not too hard to solve that equation for all integers, and notice for P of 0, we'll get the origin, and then we'll get 1, 0, minus 1, 0, 0, 1, and 0, minus 1. And those are our only integer solutions. So now let's look at that on a graph. Okay, so that's going to give us this point right here, and then all 4 points up here on these axes that are 1 unit away from the origin. And now it's not too hard to see that only a single 4-point subset of this makes a square, and it's the one that looks like that. Okay, so in this case, a of 0 equals 1. So now let's look at P sub 1. Okay, so now, using the fact that P0 is contained in P1, we can write P1 as P0 union all integers x and y, those coordinates, where x squared plus y squared equals 2 to the first power. So notice that's going to give us the origin plus minus 1, 0, 0 plus minus 1. So notice this bit is from P0. But then the only integer solutions to x squared plus y squared equals 2 are the following. So here we get plus minus 1, plus minus 1. So now let's graph that. So here we'll have the origin. We'll have these points right here, which were in P0. So all of that is in P0. And then we have these points up here as well. Good. So now what I want to notice is that everything inside of this blue square was a member of P0, and what we've added onto this is these 4 points here to create P1. And notice as we do that, we have 4 more squares. So we have a square that is outside of everything. So that's one of them. And then we have these 4 squares that include the origin and one of our new points. So 1, 2, 3, 4. So all in all, we have 5 squares. So A1 is 6 and A0 was 1. So we gained 5. Okay, so now let's look at maybe one more example before we get our guess. So we'll look at P2. Okay, so now we have P2. So P2 is going to be P1 union this new set, which is the solutions x squared plus y squared equals 2 squared. In other words, x squared plus y squared equals 4. And notice, in this case, that's going to give us 4 more points. So we have all of these that I've overdone in red. That was our original P0. Those that are overdone in blue, that's our P1. And then those are our new points that we add in to get P2. So we have plus minus 2, 0, and 0 plus minus 2. So let's see what that gives us. So that's going to be like a point right here, a point right here, a point right here, and then a point right here. So those are our 4 new points in P2. And notice we get 1 new square, which is given by connecting all 4 of those new points as follows. Good. And then notice we get 4 additional squares that is made by connecting these points. So we get the overall square and then these 1, 2, 3, 4 new squares. So in other words, we have A2 equals 11. So it looks like at each step we get 5 new squares. So we have A3, seems like it should be 16, and so on and so forth. So if we get 5 new squares each time, then maybe our guess should be that AN is 5N plus 1. And that's indeed what we'll prove. But before we get to proving that, we need to look at solutions to this equation so that we know we're getting the right thing for our sets Pn. So that'll be our first goal. So to get us started with our careful solution, we're going to prove the following claim. So the only integer solutions to the equations x squared plus y squared equals 2 to the 2k are xy equals plus minus 2 to the k comma 0 or 0 comma plus minus 2 to the k. So those are happening on the coordinate axes. And then if we have an odd exponent here, x squared plus y squared equals 2 to the 2k plus 1, we get xy equals plus minus 2 to the k plus minus 2 to the k. So those are happening on the 45-degree lines away from the x-axis and the y-axis. Okay, so the proof of this will be by induction. So we have 2 base cases, and those base cases depend when k equals 0 in these 2 equations. So this first equation, when k is 0, is equal to x squared plus y squared equals 1, but this clearly only has solutions x, y equals plus minus 1, 0, 0 plus minus 1 as needed. So it's clear that those are the only solutions, because notice any other solution would bring you to a number that is larger than 1, which means that the other term would need to be negative, but that's impossible if these are integers. Okay, good. And then our other base case is x squared plus y squared equals 2. And again, that only has integer solutions xy equals plus minus 1 for a similar reason. Notice if x or y are bigger than 1, then that would make the other term imaginary number by necessity. So we have our base case. So I'll clean up the board and then we'll get to the rest of the induction proof. So we proved our base case and now we're ready to finish it off. But before we do that, we need to recall the following observation, which is easy to prove, and that is for any integer x, we know that x squared is congruent to 0 or 1 mod 4. So in other words, we cannot have a perfect square be congruent to 2 mod 4 or 3 mod 4, only 0 mod 4 or 1 mod 4. So we'll use that as we finish this proof. So let's look at the even case. So let's suppose this is true for some k. Let's look at the equation x squared plus y squared equals 2 to the 2k plus 2. Good. And now let's reduce this mod 4. So that gives us x squared plus y squared is congruent to 0 mod 4. Great. But now we know that x squared and y squared are both either 0 mod 4 or 1 mod 4, but notice neither of them are allowed to be 1 mod 4, because then we would have a 1 or a 2 over here. So that tells us that x squared and y squared are both congruent to 0 mod 4. Good. But what that tells us is that x and y are both even. So if x squared and y squared are both multiples of 4, that's what this means. That means that they are both even. But that tells us we can write x equals 2x naught and y equals 2y naught. And now plug that back into this equation. So that will give us 4x naught squared plus 4y naught squared equals 2k, 2 to the 2k plus 2, which tells us that x naught squared plus y naught squared equals 2 to the 2k. Good, but what that tells us is that x naught and y naught must be of the form that's given by this up here by our induction hypothesis. So let's write that down. So x naught comma y naught is equal to plus minus 2 to the k, 0, or 0 plus minus 2 to the k. But now recall that x and y were twice x naught and y naught, so that makes xy equal to plus minus 2 to the k plus 1 comma 0, or 0 plus minus 2 to the k plus 1, which is what we needed. Okay, I'll clean up the board and then we'll look at the odd part of this induction proof. So we've proven this even statement is true, and now we're ready to prove that this odd statement is true. So again, we have both of our base cases, including the one that starts off all of the odd cases, and we'll use this observation again. So let's suppose this is true for k, and then we'll prove that it's true for k plus 1. In other words, we want to look at the equation x squared plus y squared equals 2 to the 2k plus 3. That's what we get if we plug k plus 1 into that. But now we're going to reduce this mod 4 again. These steps are actually going to be exactly the same. So that means x squared plus y squared is congruent to 0 mod 4. Because this up here is obviously a multiple of 4. But now what we can do is use this observation. So we know x squared and y squared must both be congruent to 0 or 1 mod 4. But we know that neither of them can be congruent to 1 mod 4 because we wouldn't get a 0 over here. So that tells you that x squared and y squared are both congruent to 0 mod 4. But what that leads us to say is that x and y are both even, which tells us that we can write x equal to 2x naught and y equal to 2y naught, and then we'll do exactly the same thing that we did in the last step. So we'll plug that back into this equation, so that gives us 4x naught squared plus 4y naught squared equals 2 to the 2k plus 3. Good. But then that gives us x naught squared plus y naught squared equals 2 to the 2k plus 1, just by dividing both sides by 4. But then, by our induction hypothesis, that tells us that x naught y naught must be of the form plus minus 2 to the k plus minus 2 to the k. It's that type of ordered pair. But then multiplying all the entries by 2, because we know x is equal to 2x naught, and similarly for y, that gives us x comma y equals plus minus 2 to the k plus 1 plus minus 2 to the k plus 1. And that finishes the proof. So what this really tells us is that Pn plus 1 is equal to Pn and then 4 additional points. And that's exactly what we'll use to prove our claim that we had before. Okay, I'll clean up the board and then we'll get to that. Okay, so this is how we'll state this claim that we had before. So we have a of 0 is 1, and that was pretty clear from the picture that we drew before, and that's backed up even more by the proof that we just did. And then we have an is equal to an minus 1 plus 5, and that means we get 5 new squares at each step. And we'll prove this again by induction. So we'll look at case number 1, which is if n is even. Okay, good. And that means what we can do is we can write P2k is equal to P2k minus 1 union some new points. And those new points are plus minus 2 to the k, 0, comma, 0 plus minus 2 to the k. Okay, good. But now let's make a picture here. So the picture that we'll make will be as follows. So we'll go up here to, this is one of our new points. So this is 0, 2 to the k. Good. Then we'll go down here. So this is 0, negative 2 to the k. And then over here is 2 to the k, 0. And then back here is negative 2 to the k, 0. And then we know that the last stuff that we added to this picture were right in between here. So here we have in the middle and this point right here. And in the middle here and this point right here, there, and there. So this is the point 2 to the k minus 1, comma 2 to the k minus 1. And so that occurred in the p2k minus 1 case. Okay, and so now what we can see is that if we form this into a square, everything in here is part of p2k minus 1. Great, and we know inside there we have a certain number of squares, and what we need to do is count the new squares. So notice we obviously have one that uses our new 4 vertices. So what we want to do is find more that use one of the new vertices and then some of the old vertices. So let's do that. So let's suppose we have a new square with this point right here, 2k, comma 0, and old vertices. Okay, the edges of the square that includes this new vertex need to be along these two rays. And that's because otherwise we would be outside of the set altogether. So notice, if one of the edges went that way, back this way along the axis, then our other edge would have to go straight up or straight down, but that's outside of this square. And if you move this any other angle except for right along this ray, you would have a similar problem. So in other words, our new square has to be along this edge and this edge. Great, but there are only 2 additional points along this edge and 2 additional points along this edge to choose from. One is the brand new point that we added, which it corresponds to our large square, and the other one is this point right here. And so that means if we have a new square from this vertex, it must include this point right here and this point right here. And then what you can do is check that the origin completes that into a square. And that's not too hard to do. Good. And then you make a similar argument for the rest of these 4 vertices. So there's another new square. And then there is another new square. And then finally, here's another new square. So that gives us 5 new squares. So, in other words, in this case, our new square has vertices. So 2k, comma 0, 2k minus 1, 2k minus 1. 0, 0, and 2k minus 1, negative 2k minus 1. So that would be this square right here. Good, and you can make a similar argument or just an argument via symmetry for all of the other 4 parts of this. So in other words, we have 5 new squares, which tells us that a2k is equal to a2k minus 1 plus 5. Okay, good. So now I'll clean up the board and we'll look at the similar case when we have n is equal to an odd number. Okay, so now we're ready for our second case, which is when n is odd. And in this case, we're going to use p 2k plus 1 So that's equal to P 2K union 4 more points, again, built upon our previous claim. So in the 4 new points in this case are plus minus 2 to the K, plus minus 2 to the K, like that. Okay, good. So now we can make our picture just pretty similarly as before. So our new points are given out here like this. So it will be this point right here. So this is 2 to the K, 2 to the K. This point back here, which is negative 2 to the K, 2 to the K. This point down here, which is negative 2 to the K, negative 2 to the K. And finally, this point over here, which is 2 to the K, negative 2 to the K. Okay, so those are our new points. And then recall that the last points that we put in other words, the ones from P to the 2K, will be along the coordinate axes, because the even solutions always correspond to the coordinate axes. So now we can fill this in like that, and notice everything inside here is part of P sub 2K. So now we want to count the new squares once we have the addition of these 4 vertices. So we obviously have the large square that envelops everything. That's an obvious choice. But now let's suppose that we want a new square using this vertex and then all old vertices. And so by an argument similar to what we did before, we know that a square containing this vertex must also go along these 2 edges. So notice if it doesn't go along those 2 edges, it will go outside of the given set. Okay? So that means we only have 2 more choices for vertices along this edge. This one that we've already used and we've counted that new square, or this one right here. And similarly, in this direction, we have this one that we've already used, or this one right here. So we have that new square. Great. So that means if we have a square with vertex 2 to the K, 2 to the K, and no other new vertices, it must be this square right here, 2 to the K, 2 to the K, 2 to the K, 0, 0, 0, and then 0, 2 to the K. So in other words, it goes like that. Good. So just as before, that gives us 4 additional squares of that type, which I've drawn in blue. So in the end, we have 1 large square enveloping the whole thing, and then we have 4 more new squares. So that gives us 5 total new squares. In other words, we've just shown that A sub 2K plus 1 equals A of 2K plus 5, which finishes the proof of this claim. Okay, I'll clean up the board and then we'll have a summary. So we've just established this one-step recursion on the number of squares, in other words, kind of our goal, and we see that we have a starting point, A of 0 is 1, and then A of n is A of n minus 1 plus 5. And so it follows from this that A of n is 5n plus 1. And that's pretty easy to see by induction if you want to, but I'll leave it to you to do that, because that would be by far the simplest step of anything that we've done in this whole video. Okay, so that's the end of this solution.